Welcome to another video. If I'm allowed to graph these functions, I can easily use Desmos to graph this, and I notice that the two of them will meet at 3 different points, which means there are 3 real solutions to this equation. Now, by just observing and trying numbers, you'll be able to see that x equals 2 is a good answer, because 2 squared equals 2 squared. That makes sense. Also, x equals 4 is a good answer because 4 squared is the same thing as 2 to the 4th, which are both 16. But there's a third answer that is missing, which the graph is going to give you, but you cannot just guess. So, and by the way, how do we know that only 2 and 4 are the numbers that would work? What if there's another integer that might work? So these are the problems with just trying out numbers because you're not sure if you found all the solutions. I'm going to try to show that there are no other solutions by the way I'm going to solve this, which is similar to the way I solved it. And ultimately, I'm going to use the Lambert W function just to verify everything and find that other one that is missing. That is not an integer. Let's get into the video. So my first move is to do my algebraic manipulation here. I'm going to say that just by looking at these expressions, the right-hand side is a power of 2, assuming x is an integer, okay? If x is an integer, then the right-hand side is a power of 2. The left-hand side must be a power of 2, purely. If it's purely a power of 2, it means x must be a power of 2. Okay, it cannot be a power of anything else because there's only 2 as the base here. So this has to be a number that can be written as 2 to something. We just don't know what something is. So what we're going to say is, we're going to say let x be equal to 2 to some integer. Let's call it k. So if we rewrite this equation, then we're going to say 2 to the k equals 2 to the x. Okay. No, not 2 to the k. We got to square the left-hand side is x squared. If x is 2 to the k, then this has to be 2 to the k squared. Oh, do you see that? So this tells us that 2 to the 2k equals 2 to the x, which tells us that x must be equal to 2k. Nice. But again, we said x equals 2 to the k. So x equals 2k by equating the exponents, but x is also 2 to the k. So that means that we can find all numbers, all integers that satisfy this equation. Okay? Now, let's start with this idea that k is, in fact, let me start from -2. Let's just see a range of numbers. Okay, let's make a table. Okay, let's do k, and let's do 2k, and let's do 2 to the k. Okay, so I'm going to choose numbers here. When this is -2, -1, 0, 1, 2, 3, 4. Okay, so we're going to have, let's see if these can be equal. So 2k is going to be -4. 2 to the k will be 1 over 4. That's 2 to the -2, which is going to be 1 over 2 squared, which is going to be 1 over 4. So these two are not equal. Remember, we need these two to be equal. So we're going to go here. So this is much less than this. If we go here, we're going to get -2. And this is going to give us 1/2. This is much less than this. If we get 0, this is going to be 0, and this is going to be 1. This is less than this. If we get 1, we're going to have, what will we have? We're going to have 2, And this is going to be 2 to the 1, 2. Oh, they're equal. So when k equals 1, these two are equal. So k equals 1 is good here. Okay, k equals 1. Okay, we got one. We're going to come back. Now we go here. 2k is going to be 4. And then 2 to the k, oh, it's also 4. So k equals 2 also works. Which means k equals 1 implies that x is equal to 2 times 1, or 2 to the 1. Okay, let's write 2 to the 1, which will be equal to 2. This also implies that x equals 2 to the second, which gives us 4. Let's see if we can find more numbers. So here we have 3. That's going to be 6, and this is 8. This is going to be 2 to the k, 8, and this is going to be 16. Okay, now I'm not going to show you, but by induction, you can show that for any value of k greater than 4, we can show by induction, we can show by mathematical induction that for k greater than 4, 2k is less than 2 to the k. Maybe I should show it. I didn't plan to do this, okay? Okay, but so if you are not looking for the third option, you're just looking to show that the only two numbers that satisfy this equation are 2 and 4. You can do this by mathematical induction. Firstly, we're going to say that, look, let's start with the base case. Any k, where k is an integer, okay? Any k that's greater than 4, you're going to have this. So let's say, base case. This is a base case. Base case, you have k. Let's put it here. Let's say proposition, we have k to be 5. P of 5 is such that 2 times 5 is less than 2 to the 5. Is this true? Absolutely, this is true. You can see that 10 is less than 32. So this is our base case. We have shown, because that's this first number that is greater than 4. So this is a claim. Now we want to show that any other number it is true for any other number that's greater than 4. So suppose it is true P of n, suppose the proposition that n is greater than 5 and therefore 2 times n is less than 2 to the n is true. Then 2n is less than 2 to the n. Okay, we're going to say that this statement is true. That's what we're supposing. Now we will need to show that any number after n is true. This statement is true. Okay, now I didn't plan to do this, so if this looks messy, forgive me. So what we have is, we say, then the proposition for n plus 1 is such that we're going to say 2 times n plus 1, no, what did I say? Yeah, 2 times n plus 1, we want to show that it is less. It needs to be less than 2 to the n plus 1 is equal to, let's do this. 2 times n plus 1 is equal to 2 times n plus 2. I know that if this is true, 2n is less than 2 to the n, then I know this is less than 2 to the n plus 2. Because this is less than 2 to the n, so I just switched it, changed it to less than. But I know that 2 to the n plus 2 is actually less than 2 times 2 to the n. This is less than 2 to the n times 2. And this expression is 2 to the n plus 1, which is equal to 2 to the n plus 1. So clearly, as long as you have your n to be greater than 4, if 2 to the n is less than 2 to, if 2n is less than 2 to the n, then 2 to the n plus 1 is less than, 2 times n plus 1 has to be less than 2 to the n plus 1. And that's it, we're done. So I know there are no other integer solutions. Okay, now that we found the integers by algebraic manipulation, let's find the non-integer that is also negative using the Lambert W function. But there's something I want to show you. I think I've shown this before in a previous video, that you don't need Wolfram alpha to be able to approximate these values. You may use a power series to find the approximate value. So if you want to find W, let's actually write it somewhere here. Okay, you see, W of any quantity, let's call it X, can be evaluated using this expression. It is the sum from n equals 1 to infinity of just negative n raised to power n minus 1 divided by n factorial times x to the n. Okay, so if you have several terms of this, by the way, the quantity you want to evaluate using the Lambert W function is what you call the x. The number of terms you want to add together is what you call n. So if you just want to take the first term, your answer is definitely not going to be accurate. So the more terms you apply, the better. Now, if you try to evaluate this, when n equals 1, you're going to have negative 1 raised to power 0 over 1. Minus 1 raised to power 0 is 1 over 1, which is 1. X to the 1, so it's just x. So the terms would be, let's write it here. W evaluated will be equal to, using this formula, you're going to have x. If you do x n equals 2, you're going to have negative 2 raised to power 1 over 2 factorial. Negative 2 over 2 is negative 1 times x squared, so it's minus x squared. The next one is going to be plus 3 halves over x cubed. The next one is going to be when n equals 4. Let me try that. So this is going to be negative 4 raised to power 3. That's going to be negative 64 over, what is n factorial? That's 4 factorial is 24. What divides the two of them? 8 divides this. This is going to be 8. 8 here is going to be 3. And it's going to be negative. Okay, so this is going to be negative 8 over 3 x to the 4th plus. So you just have more terms going. So I hope I didn't make a mistake. If I made a mistake, maybe I'll fix it when I'm editing. But this is basically what this series is. Just plug in the value you want to plug into the product's log function or the Lambert W function, and you'll be able to approximate even using Desmos. Okay, so now let's solve this, assuming that the value we're looking for is negative, because we're not looking for the positive values anymore. We already found them. They are integers. So let's say we want to solve this now. To find x such that x is less than 0, x is a negative number, now I'm going to be using natural log, so I cannot be taking the natural log of both sides because I can take the natural log of a negative number. So I'm going to say let u be negative x, so that negative u will be equal to x and negative u squared will be equal to x squared, which is, from here I can say that u squared equals 2 to the negative u. So that 2 ln u equals negative u ln 2. I put these two together, I have 1 over u ln u equals negative ln 2 over 2. I left the negative here. We can rewrite this as u to the negative 1 ln u equals negative ln 2 over 2. Trying to see if I can save space. Okay, let's do more here. What does this mean? It means I can write this as e to the ln of u to the negative 1 times ln u equals negative ln 2 over 2. I can bring this negative 1 down here. I can move this ln u here. So I have ln u e to the negative ln u equals negative ln 2 over 2. So now I need these two to have negatives. This has a negative already. I need a negative here. It means I have to multiply both sides by a negative, which leads me to negative ln u e to the negative ln u equals, since I've multiplied both sides by a negative, this negative disappears and you have ln 2 rather, over 2. Now we can use our w function, because now if I take the w of both sides, I'm just going to get this guy. Negative ln u equals the w of ln of 2 over 2. The natural log of 2 we can easily compute and divide it by 2. If you divide that by 2, you're going to end up with, let's move the negative here. Ln of u will be negative w of, this quantity should be 0.34657 approximately. Okay, we're just going to stop at 5 decimal places. So this is what you're going to go plug into your x. You're going to get an approximate value. Now, if you want to get more accurate answers, you can keep pushing and generating more terms. So we stopped at n equals 4. You can do n equals 5 too, which would be negative 5 raised to the power 4, which is going to be 625 divided by 5 factorial, which is 120. So the number is going to explode quickly, okay? But you can do that on Desmos. So there we go. So we're going to have u has to be e to the negative. Is anything missing? No. W of 0.34657. And that's it. Now, we're not looking for u. Remember, we're looking for x. And initially, we said that x equals negative u. So to find our x, it's going to be negative. You know, this can never be negative. This expression, because it's an exponential function, it cannot be negative because e is positive. So we have, but if you now bring in this x equals negative u, then it means we have a negative number as our answer. W of 0.34657. Okay. So what does this whole expression give us? I think the answer to this should be, if you square this number, you're going to get 2 to this number, which is fascinating. Okay, now if you did not make an assumption that it was negative, you didn't have to make this substitution and you're going to get a quantity. So the argument you're going to be getting here would have been a negative number. We would have pushed you into this region of the Lambert W function, which means you'll be getting 2 answers. The first answer is going to give you what would ultimately lead you to 2. You're going to get x equals 2. And if you use the other branch, which is the negative 1 branch, then you're going to be getting x equals 4. But what we just did now led us to the answer that gave us this quantity, negative 0.7661. There's only one answer. Never stop learning. Those who stop learning, stop living. Bye-bye.